Hey students, welcome back. Good to have you here. We are going to be here learning section 5.3 of your chemistry book, and we're going to talk about spectra today. All right, so we're going to idea of why does a neon sign work? Neon signs are bent tubes with neon gas inside of glass. And then what makes them glow? What gives them the characteristic color of blues, light blues, greens, yellow, oranges, and yellows, even reds and pinks? What gives it that specific color? So that's what we're going to be talking about today is why certain gases or certain elements may be a different color based on certain circumstances. And this is where the chemical properties are explained, and this is why the quantum mechanical model helps us understand those more accurately than previous models like the Bohr model and Rutherford's model. All right, so light. Light is measured in a couple different ways you can think of it. You can think of light in terms of wavelength and frequency, are two ways to think about it. The amplitude of a wave is how high and how low the crest may be. How high the height is and how low the crest is relative to a position that's usually zero on an XY graph. The wavelength, represented by the Greek letter L, which is lambda, is the distance between the crests. So let me show you a picture here in a moment of all that. The frequency is how many wave cycles you will see in a particular unit time, and that is the Greek letter V. We would say nu. So we write that letter out of kind of like a curly Q on the end there of the V. It's the Greek letter nu. And then the units for frequency are cycles per second is called a hertz. Cycles per second. So let's look at these. Look at a graph here. If you've taken any level of physical science in high school and middle school, you've seen this before. So the height of based on a zero line here, this is called the amplitude. So the amplitude is how high or how low a crest might be. So this would be the amplitude measured right there, okay? And it's an absolute value, so the amplitude is a positive value. The wavelength is the distance between 2 points, two similar points on the wave. So a lot of times you'll use the crest, or you'll use the crest heights right here, the crest or the troughs, measure between troughs or measure between crest. Okay, and the frequency is how many times. So if I pick a point here, how many times will my wave pass? So think of me standing in the ocean right here, and how many waves hit me per second? Okay, so this would be a low frequency because there's not many full cycles of the wave. So if a wave starts here, here's one cycle, here's two cycles. So this would be a frequency of 2. All right, right here would be a high frequency that you still have a similar amplitude, same height of the wave height or the trough height here, but you'll notice that it has a shorter wavelength. The distance between crest or the distance between troughs is much smaller than this, and that the frequency is much higher. So you have 1, 2, 3, 4, 5, 6, a frequency of 6. So you notice that there's a relationship between it's a higher frequency, the wavelength is shorter. If it's a lower frequency, the wavelength is longer. So if I'm in this ocean, waves are hitting me 3 times as faster as they would in this ocean right here. So that's a relationship. There is a relationship between wavelength and frequency, and that is I call the constant of the speed of light, c. The speed of light is equal to the wavelength times the wave height. Okay, so go back here and just remember the wavelength is L and the frequency is nu. I think I misstated that earlier, so I want to make sure I clarify that. Wavelength is lambda and frequency is the letter nu. So wavelength and frequency. Okay, lambda is length, L for length, lambda, length. Nu is for frequency. So the speed of light is the constant of speed of light is the frequency times the wavelength. All right, so according to this model, that this proportion that it is, there's what's called electromagnetic radiation. It includes that there's includes all types of waves: radio waves, microwaves, infrared rays, ultraviolet rays, visible lights, gamma, and X-rays. And they all travel in a vacuum. All of these waves will travel in a vacuum at the speed of light, or 2.998 times 10 to the 8 meters per second. Okay, so sunlight consists of light with a continuous range of wavelengths and frequencies. Okay, when it passes through a prism, the different frequencies separate into what are called spectrum. Spectrum of color spectrum would be one portion of the electromagnetic spectrum. Okay, so the visible spectrum, red light has the lowest wavelength and the lowest frequency. Excuse me, red light has the longest wavelength and the lowest frequency. So here's the electromagnetic spectrum. You'll notice on this, you'll see frequency. That is how many times it passes by in per second. So the second to the -1 means per second. And the wavelength measured here in meters. Okay, so what is very noticeable here is that you'll see that the electromagnetic spectrum in the middle is visible light. This is what we can see. But there's many other types. So on the lower frequency end, on the high frequency, on this end down here, with the longer wavelength and the lower frequency, you have radio waves, followed by radar, microwaves, and infrared. That's whether you might wear the goggles. You can see night vision goggles. Ultraviolet is what comes from the sun. X-rays, when you get your teeth, go to the dentist, or have a bone if you've broken a bone. And then gamma rays. Gamma rays are the rays that, if in a practical purpose, are used for curing cancer. Okay, so all of these are, you'll notice that as you go, the wavelength gets smaller as the frequency gets bigger. Let me say that again. The wavelength gets smaller as the frequency gets bigger. Okay, so meaning that the distance between the wavelength, is smaller as the frequency, the more times we see it, gets bigger. So we saw that here. As the wavelength gets smaller, we see a higher frequency. Going the other direction, as the frequency gets smaller, the wavelength gets bigger. So you see that there's a bigger wavelength here, bigger distance between waves here. Okay, but the frequency is lower. As the frequency increases, the wavelength decreases. Okay, so this is what's called the electromagnetic spectrum, and you should be familiar with some of these ranges of numbers, knowing that radios are in 10 to the 2 meters, and visible lights in 10 to the -6. And so you should know that range there, at least know on the beginning and the ends of them. All right, so calculating the wavelength, we use that formula that we had before. If we want to calculate the wavelength of yellow light emitted by the sodium lamp, often big lamps on highways, they used to be sodium lamps. Many times they're being replaced by LEDs, but sodium lamps give a very bright light to see in the evening and the nighttime. So what you would do is you want to calculate the wavelength if you're given the frequency. And the frequency is 5.10 times 10 to the 14 hertz, or 5.10 times 10 to the 14 per cycles per second. And that's what a hertz is. All right, so you write down what you got. You have the frequency. The given is the speed of light, 2.998 times 10 to the 8th. And here's your wavelength. That's what you're looking for. You grab your equation. Speed of light equals lambda nu. Okay, and you solve for lambda. You're looking for wavelength. That's what it's asking for here. So we're asking for wavelength. Solve for wavelength, and you report your significant figure. So the wavelength of that sodium light is 5.88 times 10 to the -7 meters. Okay. All right. So what is the frequency of radiation of a wavelength? Now we're given a wavelength, and now we want to know the frequency. So that is, you would reverse your path there. So we'll do that one in class if we haven't already. Now we're going to talk about, we've talked about wavelength spectra. Now we're going to talk about atomic spectra. And this is where kind of we've gone from physics, and we're going to bring it more into specifically the physical chemistry of this chapter. So what causes atomic emission spectra? Okay, so when atoms absorb energy, electrons move to higher energy levels. You can think they move from an s orbital to a p orbital, from a p orbital to a d orbital. Okay, these electrons then lose energy by emitting light. So as they gain that energy, they move from one orbital to another, and then they lose that energy by giving off light to lower energy levels. All right, so let's look at an example of this. A prism separates light into colors it contains. So when white light passes through a prism, it changes into the different colors of the rainbow, RGB, as you've learned. Red being the longest wavelength, and ultraviolet being the shortest wavelength of the rainbow colors. Okay, when a helium, rather than light, now we're going to think about helium, just helium gas. When light from a helium lamp passes through a prism, discrete lines are produced. So rather than a whole sort of gradation from red down into orange, down into yellow, into cyan, into green, into kind of blue, blue, into violet, into purple. Okay. Rather than that gradation, when you pass an atom through there, you have these distinct lines. Distinct lines are produced. So distinct patterns. I want you to think about atoms are going to have distinct patterns of lines that they'll leave on the screen there as they pass through a prism. All right. So the different frequencies of light emitted by an element separate them into their discrete lines, and those are called atomic emission spectrum of the element. So, for instance, you'll see this would be what mercury when it's passed through a spectrum, and nitrogen. Okay, so here's the explanation. How are these frequencies of light and the related changes into their energy colors related? How are they related? How is the type of light you're seeing related to the frequencies of light? All right, so we talked about in the Bohr model. The Bohr model is that model with the atoms moving around in an orbital fashion. It's one way we can understand it. The lone electron in the hydrogen atom will have certain amount of specific energies. When the electron has its lowest possible energy, called ground state, that's where it wants to be. It wants it to be in its lowest state. Okay. When you excite that atom, it's called an excitation. Okay, the word excite is in there. Excitation of an electron is by when you send some energy, you excite that hydrogen atom, it absorbs that energy and it raises from a ground state to an excited state. And that's when a quantum of energy forms the light as the electron moves from one energy level to the next. And when it drops back down, after it releases that energy. So the light emitted by an electron moving from higher to lower, so it's excited, moves to higher, and as it releases that energy and moves back down to the lower energy level or orbital, it has a frequency proportion to the energy of change. So the amount of energy that is changed from a higher state to a lower state energy level is proportion to the frequency of energy given off. So what that means is you have three groups of lines in the hydrogen spectrum that correspond to the transition of the electrons. Okay, so here is what you have these three different series. Okay, it's called the Lyman series, the Balmer series, and the Paschen series. And you'll see that they'll have these lines will form as electrons move. They've moved up a level, and then when they've moved back down. See, each one of these are moving back down. These energy levels will form these distinct lines on the screen. So what we need to see is that there's a pattern, a predictable pattern where you can identify an element based on what spectral lines you might see on a screen. Okay? So how does this differ? How is this type of quantum mechanics understanding different from classical mechanics? And this is where we have to introduce Albert Einstein. He successfully explained that by experimental data, proposed that light could describe as packets or quantity of energy. The quantity behave as if they were particles. Light quanta are called photons. Now, this can be a little confusing because we just learned protons. These are photons. Light quanta, these packets of energy, are called photons. And in 1924, an equation was developed that predicts that all moving objects are like wave-like behavior. So what we have here is we have the quantum view is that light is particles, and then we have the wave view that objects are like waves. So we have a seemingly contradiction between two scientists. One says it's made of particles, light's made of particles. The other one says it behaves like a wave. So today, the wave-like patterns and properties of beams, electrons are used to magnify objects. So an electron scanning microscope would be one of those where you can see things, images very clearer because they can use the changes in these energies to their favor to see something as the eyeballs of this small, very small light. All right, so here's how the classical mechanics and quantum mechanics may differ. Classical mechanics adequately describes the motions of bodies larger than atoms, planets, spacecraft, moons, the universe, how things work on. So anything you can see is classical mechanics. But when we get to the atomic level, it gets a little weird. Quantum mechanics describes the motion of the subatomic. So what you think of Newton's three laws do not apply at the subatomic level. There's also almost like two different universes or two different worlds. The classical mechanical level at the macro to mesoscale, and at the micro subatomic level. These are described as atoms and waves. So here's where we're going to end up here today, the Heisenberg uncertainty principle. This states that it's impossible to know where the position of a particle is and its velocity at the same time. Okay, you can't know how fast an electron is moving and where it is. So that's where that cloud model comes in with these orbitals, these spheres of s orbitals and p orbitals that are tear-shaped, and d orbitals are kind of fatter tear-shaped, is that this is probably where the electron is. If you know its velocity, you don't know where it exactly is. And if you know where it is, you don't know its velocity. So this is a limitation in understanding. That's why it's called an uncertainty principle. This limitation is critical in dealing with small particles like electrons. Limitation doesn't matter for ordinary size objects such as cars and planes and people like you and I. We can know how fast we're going. We know how fast they're going, where a car is, and where it is. Hence, our GPS systems on our phones work that way, to almost down to a less than an inch accuracy. But that is not possible for an electron. So here's a little bit more of what happens here is as a photon collides with an electron. Before the photon strikes an electron during an attempt, you can observe and see it. You can see the electron where it is. Okay, but once that photon strikes it, the impact changes the direction of the electron's velocity, making it uncertain. Okay, so this is the uncertainty. So what I need you to understand from this main point, this is the main point I want you to understand from the Heisenberg uncertainty principle. There's a lot involved with this, and actually a lot involved with all that we've done in this chapter, but is that you don't know where an electron is and its speed at the same time. That's what that says. So that's it for this chapter. We will be going over some more of how to write out electron configurations. We'll be working on these this chapter, and then before we move on to the chapter on the periodic table. So that's it for today. I'll see you soon.